image. Okay, so as Alan said, I will try to present today a few insights about the life of Coq, mostly Coq development team, from the perspective of Caml users. So I'm a member of INRIA team called Pierre Letouzey, and also from the Paris Diderot University as well. So also, as Anna said, since the audience can be quite mixed, research and non-research, I've tried to start by kind of identity card for this software I will speak about. So Coq, what is it? It's a proof assistant. So more precisely, we can also decode this term of proof assistant as something that will do type checking for a specific, so either logic or functional language as you prefer to see them. We know that it's about the same thing to speak of a language, of a logic or a language. It's Curie-Howard isomorphism. And at the same time, it can also be seen as a compiler for this language, and indeed we will have a runtime computation system inside. So when has it started? I think in the README it speaks about 1985. Well, it's almost as old as Caml. I think it started even before Caml Lite. Well, it's a long time ago. There was already a long sequence of INRIA teams that has worked on this software, but also French university guy like me, and we tend to have a few and hopefully larger and larger community of contributors worldwide. I can mention Nijmegen in Holland, I can mention a few places in the States, and we hope to have more and more persons involved. The license of the software is LGPL, so if you want to contribute, please do. It's open source. The size is, well, rather large, I would say, compared to many other Caml softwares. So around 200,000 lines of code for the source part, written in Caml, or Caml variants, and about the same forming the standard library written in Coq. The users, so it's hard to count because it's open software, so everyone can grasp it without our knowledge. But one metric can be the number of persons registered to the mailing list, and it's counting in more than 1,000. And we already have a few nice feats, or many nice feats done with this software. I can mention, of course, the 4-column theorem by Georges Gontier and his team. I can mention, of course, the concert certified C compiler by Xavier Leroy and his team, and well, things like that. So let's try to, well, justify is always difficult because it's also historical reasons. It's also the fact that Caml and Coq started at the same place and so on. But okay, let's try nonetheless to answer a bit the question of why Caml. So roughly, Coq's main job is to play with abstract syntax trees. We, as I said, it's, well, from a faraway perspective, it can be seen as a compiler, more or less. So playing with VSTs, I've tried to be a bit more precise here and say that the core of the job of Coq is playing with what we call terms. And those terms, it's a unified notion of formulas, of functions we can program in Coq, of proof fragments. Sometimes we do not want to provide in one shot the whole term, but build it interactively, piece by piece. And so we have this construction of terms by many phases. First, of course, we start from the user textual input, a string, and we pass it in something structured, a bit structured. In the internal jargon, we call that const exp. const is because the logic is calculus of inductive construction, so you will see const construction a bit everywhere in the sources. So we start with expression models. Then we try to identify identifiers, and just decide where those identifiers lies, in which file, and so on. It's kind of resolving global constant names. Then we have a notation system, we try to extend them, and we end on another AST, internal AST. Then a few other refinements on those AST take place, like filling implicit arguments, like compiling pattern matching in some more primitive pattern matching, and then finally we just verify that the terms we obtain are legal according to a specific typing system. So then at the end we end with ASTs called const. Of course, we have many other operations we would like to do on those ASTs, like computing on them, like displaying them, of course, when we are accepting them, or when there are errors, etc. And as I said, we want also to build them interactively. Of course, there are many other ASTs, like the ASTs of commands. You can ask the system many things. You have specified ASTs for tactics, the language used to build interactively those terms, and so on and so on. And so, I'm tempted to say, and I don't think it will surprise many persons here, that manipulating ASTs is right in the scope of the ML dialects in general. So now I come to OCaml precisely, and I say, roughly what we appreciate in OCaml is the fact that it has a fast compiler producing fast native code. It's quite important because, as I said in the first slide, we have a few persons pushing the limits really hard, like Porcaro theorem and so on, or C compiler. Things are tending to become quite large, and efficiency is really one of the requirements for this kind of software. And at the same time, it also provides really convenient development tools, like top-level loop, like debugger, and so on. And I think, but it's a personal opinion, that it provides a rather decent trade-off between stability. Okay, some person say it's too stable, but well, and also novelties coming in after release. So overall, we are rather, or even very happy OCaml user. So let's now try to develop a bit and come to points that are not necessarily perfect. But okay, one paradox. Okay, Coq is full of paradox. So one.
That doesn't bode well.
Well. One of the paradoxes is that when you come to inspecting each advanced OCaml features, in fact, we are not using them that much. Of course, we are using a few of them, but not necessarily, we are not, I would say, the bleeding edge guys, but well, it depends on which feature you are speaking of. For instance, here is a list, and for instance, we are using the minus vec type options that allow a type to mention itself without having subconstructors, something like that. Well, that's rather detailed, but it allows to have strange types around. Serialization, writing stuff to the disk is something really important because, as I said, we are manipulating big objects, and we do not want to recompile everything on each session. So we want to save intermediate states to the disk. So serialization, the marshalling, is used a lot, and it also brings new, not necessarily problems. We should be cautious when using some features because we need to know that the stuff we're manipulating will be, we will be able to save that on the disk. And well, we'll speak a bit of that later. Laziness, for instance, is used as just a bit. I think, for instance, when we load from disk a library, we try to avoid loading the whole file. For instance, earlier proofs are not necessarily relevant for the next jobs. You mostly want to have the types of things you have already defined. And so we say the proof is there, but we lazily not load it up to the point where the user really want to dig into these old proofs. Objects, the object-orienting layer for Caml is barely used, only in the graphical interface, and only because this graphical interface is programmed with label GTK, so it's almost obligatory to use objects there. But in the core system, in the what we call cooktop program, I don't think there is any objects there. First-class modules and GLET are not used. I would say not used yet, because maybe, and concerning GLET, will probably be users soon, but for the moment, we have not crossed the river yet. And a last feature that we are really fond of is native code dealing, so thanks Alain and a few others. That's quite important for what we do, and I will come to that in a coming slide. So why are we reluctant, or not so much, but a bit, to integrate advanced features of Coq? It's because of need. So if the need has not emerged yet, well, and there is also was a more large perspective. That is, we try to help compiling Coq on many systems, and so it's not an absolute rule, but we try to support relatively old OCaml versions. So, for example, today's requirement is 3.11.2. That is not yesterday's version, and roughly, I would say, was the version that is available in the last stable version of Debian, for instance. And that's, as you may know, a criterion that can be quite harsh. But this machine, for instance, with all those display problems, is Debian stable, and I'm quite relatively happy with this 3.11.2. Okay. We also tend, on the side note, to then prefer to avoid external dependencies, to be able to build Coq without asking the user to pre-install or pre-compile himself many versions. There is a special case, one again, concerning the graphical interface that uses, as I said, label GTK, and it tends to use more and more advanced things like source view and others. So it's an internal debate whether should we accept more and more dependencies or not. When things are small, for instance, Unicode, we have a bit of Unicode support, we have a bit of XML support. When those libraries are small, we tend to copy-paste from the original development. Well, I know it's not perfect, but it also works quite well. Okay, an important point in the Coq goals is to be extensible. We try to not provide a finished, closed system, but allow advanced user to customize it a lot. So it's an important design choice. That means extensible syntax. I will come to that in a slide. And also extensible set of commands and tactics and so on. For simple extensions, we can do that directly in a Coq script file. We have notation commands that allow to customize a bit the display of the terms. There is a tactic notation command that allows to customize a bit the appearance of those tactic elements. There is also a dedicated sublanguage called LTAC, allowing to create ad hoc new tactics. But for more advanced needs, those features in the middle of the slide show their limits, and we provide to advanced users the ability to design new Caml code and link it with Coq itself. And so that's a place where we are quite fond of loadable plugins, and so it turned out now to be doable with native code. It's working quite well. That's, for instance, where to complement my discussion on the OCaml version, we were rather early adopters of this native code DIN-link, early adopters of OCaml, I think it was 3.10, something like that. We also had a few glitches with Mac OS system and so on. Okay, extensible syntax. So one of the things we are using a lot is the Caml P4 tool, and it provides us an extensible LL1 parsing engine. Okay, I can probably dedicate a whole talk to this parsing technology. I will try to sum up that and saying that it's working. We are actually doing things a lot with that, but at the same time it's not ideal. For instance, when you want to do, well, from time to time you have to factorize a few grammar rules by hand, the left part of the rules and so on. So I'm tempted to say that it requires the abilities of something like Hugo Herbolin to really grasp the whole power of the system. And not everybody is Hugo Herbolin around. Oops. And at the same time, we do not have ready-to-use alternative. I think Hugo, one more time, made experiments with GLR parser, but it was not so satisfactory. Maybe we should try again with state-of-the-art things. But well, I think what was problematic was this notion of extensible. We want to have a grammar and add a few rules and continue, and add a few rules later and continue. And it's not that easy. Just a few words to say that we are just in the middle of those versioning question of Caml P4. So now, nowadays, Caml P4 comes in two variants: the Caml P4 distributed with the official OCaml distribution, and the Caml P4 maintained by the original author, that is now Caml P5. Well, one more time, I will probably just mention that and not speak more about that, but today we try to accept the two flavors as possible for compiling Coq. And it's also a way to, it was just a step on the way to be more abstract with respect to this parsing technology. And we are not supporting the two just to be, just to play with both of two. It was just a way to try to separate a bit, to abstract a bit Coq from its tool parser, and maybe later support something else if something else appears around. And also trying to be not too much dependent on one particular system, since the future of those two tools are not so clear. So for those that are not familiar with this grammar technology, I will just say a few words of how it works in practice. So those grammar rules are in fact declared in OCaml files. They are, as I say, side effects, declared as side effects to the parsing engine, and accumulate new rules. And in fact, those rules, as I said, are in OCaml 5 and not directly written with OCaml syntax. It would be quite horrible. And there is a syntax extension to write those rules. And in the Coq sources, we try to highlight those files by giving them a different extension. It's ML4 file instead of ML. And just to have a glimpse of what is those declaration, here is one of the grammar declaration file of Coq. It starts by this gextend over there, and then you have a few terminal, non-terminal declaration, and I was just playing to say, okay, here comes the syntax for the let of the Coq language, semicolon equal, and so on and so on. So you have grammar levels, all those stuff. So this is of course an extension, but at the right of these rows. Here comes just regular Caml code. The list more or less. Okay. Can be also a good place to give a word about the build system. Due to those syntax extensions and things like that, the code make file, or more generally the code build hierarchy, the build order is rather horrible. Some OCaml files use what we call quotations, that is inside an OCaml file we have a piece of tactic syntax or post syntax or whatever, and for just parsing those files we need already the code parser more or less. And so the code parser is itself something that we need to compile first. So this build is done by several phases just to be able to parse a file and then so know its dependencies. So even things that looks like elementary, like decoding the dependencies of a file, is not in this software. So for the moment we rely on features of GNU make, that is when you try to include a file in a make file, and if this file is not there, the GNU make try to make it, to build it. And if it fails, it tries again. And things like that. Well, at the same time, it avoids declaring explicitly those phases in the make file. Okay, it's just a way to say I'm not satisfied with the way we build Coq for the moment, and we are playing a bit around. I'm playing a bit around with alternatives. And by the way, make is not also really satisfactory when it comes to really complete support of the Coq files. As I've said in the back of the slide, Coq files are multi-sources. You have the implementation, the interface. That's not a big deal with make, but at the same time you have also multi-target, CMO, CMI, whatever. And sometimes you do not have the MLI, sometimes you do not have the .ml. Well, it's a bit tricky to handle correctly, even if, like in Coq, you want to build at the same time the native version, the bytecode version for debugging, and whatever. So I've made an experiment at using OCaml. It's way shorter than a make file, and a bit more dedicated to OCaml, of course. Okay, so it has its interest. At the same time, it's rather tricky as well. We currently have efficiency issues that are work in progress with Claire and a few others. So maybe we will switch to that in the future, but it's not that clear yet. And there are many tools around to try, like OMake, like Esponse or whatever. So things are not written in a stone. Okay, a few words about refactoring. That's one really strong point of OCaml and more generally strongly typed language. I've recently made quite a large organization to try to change a bit the structure of the sources. And it was just a matter of moving files, moving code inside files, recompiling, stopping at each error. Okay, oh, here there's something to adapt, and adapt, and adapt, and adapt, and at the end, when I've finished the compilation, I've finished the job. It was working. So, just to say a bit more, or maybe not, I think time is playing it. So that's just trying to, one more time, make Coq more component-based, and isolate the parser, and maybe later isolate other part of Coq to make them not depend too much on other parts, depend only on interfaces, like ASC definition, and not on a concrete implementation as it was earlier. And the ultimate goal, as already mentioned, we may expect someday to have a choice of parser, or at least to have a parser that is really separated from the rest, and also have Coq as a potential library usable as backend by other tools, and for that we need to expose the API and things like that. So well, that's refactoring, that's work in progress, but as I said, at least we can move quite heavily things in mini files, not the number of files, but it's very large, and big code, and we can be sure that we will not break everything completely. We will not have to retest extensively. We will not have to be sure that every piece of code will be executed someday. Some time for that is really cool. That's probably not something that's not a big lesson for the audience today, but I just confirm that. Computation. Just a few words about how we compute with those terms. Code can be used as a computing system. And we have made a reduction engine in for code terms. So the yesterday technology, I would say, was just to write it in Caml. You have your AST, you have your idea of what you want to reduce, more or less beta reduction, and a few others. And I think the first reduction machine was due to Bruno Barras. And it's already advanced stuff. It's not doing beta reduction naively. You have explicit substitution or things like that. And well, it was performing not so bad, but it shows its limits when the terms become really, really big. And so the technology currently available in mainstream Coq is to have a bytecode runtime. So your terms are translated to bytecode, and this bytecode is evaluated in a bytecode runtime that is just very similar to the Caml bytecode machine, with adaptation to the specific term. So it's a work by Benjamin Grégoire and Xavier Leroy. It's working quite reasonably. The interesting note is that it's C code. So, as I said, Coq is a whole bunch of OCaml file and a whole bunch of Coq file, but also a few C files around. Okay, it's opt-in, as would say Alain, so you can choose not to use this C code for evaluate things, but then you may expect to wait longer. And two more technology. We already have a prototype by Benjamin Grégoire one more time, is to not do bytecode stuff, but directly native code stuff. So more or less, what you want to compile, you give it to Caml. It gives you a portion, you link it, and you run it. And well, it's interesting perspectives. Oh, it's time to speak of dirty tricks a bit. So, as I said, we are not user yet of advanced things like GLET and first-class module and things like that. And it's also because we had those questions of advanced things from already many years. And so we developed a solution for those advanced type questions and so on. And those solutions were with what we had at the time. And so a few times it involved unsafe primitives of the system, like magic, converting an object and say, oh, I don't care, it has this other type as well. And a typical example is we have a DIN module. And so we cast things to this more or less untyped notion of object T. And, but hopefully we do not do that in just any way. We attach it with a string saying, oh, this thing was earlier, blah, 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 and we do not cast back if the string differs or anything like that. So it's dirty tricks, clearly, but a priori it's unsafe. But it's a very isolated place, and as I said, dynamically checked against these strings. So I've not heard of any bad behavior of this DIN module around, but nonetheless it's unsafe. So we would like to remove this someday. And I think many solutions have been tried around, but it's hard to combine things. For instance, when you want to write to disk as well. I don't know exactly, but anyway, I would be happy to discuss again with specialists about those places. Maybe it's the right time to get rid of this DIN thing for what we do. I think first-class module plus GLET or other advanced combinations may help removing this DIN thing. At the same time, as I said, it works. So you know the motto, if it works, don't fix it. we'll see. There are a few other option magic here and there, and we're not pretty proud of them, but from time to time they just do the job. I've been asked also to say a word about the Caml upgrades and how is life concerning this change of version. And as far as I recall, it has almost never been a big deal to switch from one Caml version to another. There have been an exception mentioned by Go to me. We had an issue with the order of elements when I think it was doing a set.fall or something like that. It's already quite old. And we were naughty to use explicitly the order, probably to do side effects, something like that. So well, it's our fault that the order of this fold has been reversed and oops. And the funny point is that I think this change in order followed the discussion we had with the Caml implementers after trying to specify and prove in Coq this kind of set module. And we were just saying that it's not really hard to design a nice specification of set.fall and so on if we keep the original vision of unspecified order. And, well, unspecified is something hard to specify, surprisingly. And so the things are now changed to, I think in the documentation it says that the order are presented to fold in the increasing order, I think, something like that. And, well, it's funny to have something starting in Coq that goes to Caml and then an impact back on Coq. And it's also a nice spot to speak about those Caml-Coq interactions that develop. And I like that a bit. For instance, he asked me some time ago about a new idea he has concerning implementation of set.filter. And he was asking me whether this implementation was okay. So I just adapt a bit the Coq specification, the Coq implementation of set we have, and I confirmed then that this new set.filter function was okay. So he integrated in Caml. So I think we can play more and more together like that. A few words about portability. So most Coq developers are working with Linux or Mac OS. At the same time, we have many users trying to use Windows. And of course, the Windows port of Coq is just a pain. So at least to build the binaries and distribute them, spend some time trying to use the cross-compiler that is now available due to, I think it was Sir Jones' effort first. Is it Sir Jones, I think? I don't remember. But anyway, somebody contributed the cross-compiler from Linux to Windows, and I tried to use that, and it gives me a development environment far more friendly for what I need to do. But at the same time, if you do really advanced things, you end up with nightmares about Unix compatibility. For instance, now Coq and the interface, Coq ID, are separate processes, and they are trying to communicate with each other. And for that in Unix, we have just decided to use sine and signals. So in Windows, oops. So we try to emulate that a bit. It seems to be not necessarily perfect yet. So, okay. If I have a few more minutes, we'll try to say about a few delicate programming aspects that we have considered. First one that I would like to mention is hash coursing. Hash coursing is just a technique to try to share maximally in memory your ASTs, and of course with large AST that's a very good idea. You spare a lot of memory this way, and also of time, because you can say immediately that two terms are equal because they are physically at the same spot. So it's something already quite well known. But at the same time, if you add what we want to do, for instance, saving to disk, loading to disk, from disk, and so on, it's not that easy. And also, we end up having really deep ASTs. For instance, in the NAT, in the piano, natural numbers are just successor of 0 for coding 1,000, for instance, very deep tree. And for that, I think htable.hash just stops at some depth, and so says, oh, okay, all those 1,000, 1,001, 1,002, 1,003 have the same hash. And okay, so you have an efficiency nightmare if you just do things with standard htable. So a colleague, Ilan Gisela, comes with a refined version of that, where for each subterm we make the hash come up, and we combine hashes of subparts and so on. So it's working quite well, but it was rather delicate to combine. Another delicate aspect is generic comparison. I would say more generic functions. For instance, pervasive.compare, I would say, is both a blessing because you can prototype pretty easily, do many things without too many questions. At the same time, it's a curse because each time you want to do really precise notions, saying, for instance, that your AST want to merge two constructors that will represent the same thing, but maybe one in an optimized way, not the other constructor will be the naive way, and you want to say that those two representations are equal, then, of course, you cannot use pervasive.compare anymore. And now you realize that in your code you have zillions of those pervasive.compare, and well, it's more or less too late. And we don't have yet a way to just pinpoint where are those pervasive.compare. So we have a hack, for instance, that is putting in the data structure something like a function to make pervasive.compare fail, and just be aware where the failure occurred. Well, that's dirty, very, very dirty. So, of course, if we just start today and do things again, we will just forbid pervasive.compare, but it's a bit too late. We have this historical heritage to cope with. The same with generic serialization. Marshalling output value is really nice. All those compiled.vo files are in fact just output value of stuff. But at the same time, when writing to this, it could be also a good place to do some optimizations and discard things we don't want, or put a bit of laziness here, for instance, of close proof we don't want to see yet, etc. So we would like to refine a bit more what we save to disk, and with today's tools, it's not that perfect. And also we have this question of being sure that what we load from disk is of the right type. That's another stuff. I think I will skip this question of universal level. It was just one example where pervasive.compare was not necessarily okay, at least if I just use the string plus an integer. Oh, it was very good idea to put the integer first and the string afterwards, or maybe the other way around, I don't remember, just to compare first the integer, which is fast, and compare the string later, which is slow. Well, you may want to play with those kind of tricks to get some more efficiency. An important point, I think I will end with this kind of point, is exceptions. On a large code base, where many persons have developed, exceptions tends to grow wide, I think. And many bug reports of Coq have not statistics, but more than one over three are just unquote exception occur. And most of the time it's just not found. And that's quite irritating to have those around, both for the user and for the developers that want to fix that. Okay, most of them are fixable first 5 minutes of Caml debug, or maybe more, not 5, but 20 or whatever. But okay, and the jungle of exception we raise and so on isn't currently really backtrace friendly. We most of the time catch exception, do something, launch exception again, and so on. We also may have nasty effects of the catch all try with. You catch everything and do, oh, something bad happened. But the exception can be, for instance, sysbreak. The user has sent a control C. And so you may have, I've experienced personally, places where you launch your system it goes wild. You say Control C, and instead of stopping before and saying, oh, the user interrupted me, then the sys break was catched by something like that, and the tactic succeeded. And he said, yeah, I'm happy. And he was indeed happy. It was just looking for more things, but it was not important. And so breaking this loop just made the tactic succeed. Oops. Well. Okay, so here clearly, I do think that some static analysis could really help. Or maybe not going up to the standard of Java, saying, okay, this function throws blah, 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 which is really, really verbose. We probably don't want that. But at the same time, both some declaration saying, okay, this function we know can do things, maybe at the level of the interface, telling what exceptions are expected to go from one module to another. Or I don't really know what could be done here, but something I think is to be done, and we cannot rely on the policy of the developers, because we have really two different styles around. It's very hard to remember that we have to write that this function can raise this exception and so on. Code quality, we still need to play a lot with all the static analyzer we have around. For instance, OOG of Max Guédon, or now we have a few code quality tools like ZDeclare and so on. And as I said, Magic, we should try to get rid of them. And to finish by another, oops. Oh, maybe it's a way to say that the talk is finished. So anyway, it's not important. I was just saying that we're trying to promote the use of formal method, of really complete things like specification, proof of specification, and so on. And at the same time, when we develop Coq, we do it in a rather old-style manner by testing most of the time, and so on. So this slide was just dedicated to trying to push forward the idea of using also formal methods inside the development of Coq, and that's ongoing work. And the conclusion was just that Coq is an old software, but still quite active in development. And I think it's rather unique, large-scale field experiment. We can still play with it a lot and learn new lessons and improve it and continue improving it. Thanks for your attention.
We have time for the questions.
I was just going to observe that your list of language features you do and do not use is very similar to James Street's list.
Okay.
You use first-class modules, but the rest, and in fact many of the problems you've identified are very similar.
Yeah, that's certainly a point that we are not alone in the world, and as a person we have the same requirements, of course.
So if we compare, we have a thing where we like force the type of compare to be only int to int. To int. And then if you want anything else, you just have to write the correct comparison function.
I should also admit that for many of those features, it's also because I and probably other Coq developers have not taken the time to just precisely discover them. For instance, the object layer of Caml is just, for me, terra incognita. I know it a bit, but certainly not in a position to say, okay, we can take advantage of that for doing precisely this and this and this. So I think we need to just discover those features, and maybe we can just use them more and more.
So for your problem with exceptions, you can just force people to use like option type versions.
Yeah, okay.
Which is annoying, but it does sort of solve the problem eventually. But the other thing you can do is we've got a module where you can actually get the backtrace at any point. So if you need to catch an exception and then do something and raise it, you can actually ask for the backtrace right there.
But do you have a way to just oblige, syntactically, or not syntactically, but at least by a warning or whatever, person to use this and this style of exception?
Well, the other one's not
I don't think so. So it's politics? And since we are lazy as programmers, politics.
Core has quite a principled approach to this, in that most functions that can fail will return either an option or a result type, which is like an option, but there's another branch of things that can actually error. And then there are functions that can fail, so there might be like a version that returns an option, and then often that's inconvenient, so there'll be a function which is called the same thing but _ exn at the end, which throws an exception.
You can do a bit of things with type consequence calculation or type as annotations and things like that, but well, it's not there yet. And I'm just at the place where the irritation goes sufficiently high to just decide to do something. But we are not clear on what to do. But we probably will do something.
So as I see it, there's only two parts in curve. One is the proof checker, the trusted kernel, and the other is everything else, tactics, parser, ID, whatever. So I was wondering if you could say a few words about the relative size of the two, and whether the kernel is programmed in a different way, like how much does the kernel, which is basically the only part we really care about in terms of safety, depend on those kind of borderline features like your DIN module or things like this?
Well, the kernel at least use those C file when you do some reduction. So it's already an interesting point to do we trust those C
that's
machine?
That's only if I use VM compute in my source.
Yep, indeed.
So I can perhaps avoid it.
You can opt out of this VM compute. Apart from that, I don't think those kernel files use any advanced features. Concerning the size, I don't have the figure here. I think I can just get them. Still no in here. Oops. Maybe I can. Well, anyway, I will just do the computation and tell you the answer. It's not that small. It's about 14,000 lines in the kernel subdirectory, and I think the large part is the largest increment in this kernel was the inclusion of the module system. At the same time, we are really fond of this module system, but at the same time, we also know that concerning safety, concerning the critical aspect of it has added a lot of code in it, so we'll see. And just to finish answering that, I recently had an issue with something that I was not thinking so critical, but it is. So we all say, okay, the kernel is critical, the type checker is critical, but the other parts, well, it's life if there's a bug in it. But at the same time, recently we had a bug in some large integers implementation, and it happened that this large integer implementation, just a small tool, something like big nums, but in a very small file just for doing a few things. But this file was used for parsing and pretty-printing large integers. Oops, the display of large integer was not right. So the figure you get after the computation was just false. So for me, it's critical. Clearly, there's something wrong if the user type 1+1 and gets something not 2 as an output. It was not 1+1, but it was a large number, another large number, and Laurent said, I don't think the result is correct. Oops. And it was just parser printer error, stupid error. But so things can go wrong way before the kernel, or way after the kernel. So, okay. At least, what is still true is that if those tactics do something stupid, the proof term will still be checked by the kernel, and the kernel will say, oops, there's something wrong around. Okay?
Along the same lines, you said that every bug out of 3 is an full exceptions. So are the bugs mostly or uniquely about the rest, or sometimes you still have them about the core of type checker? And the
in
other
the core.
question is the type checker written in a safer style, avoiding the catchable lines and other things that may be dangerous?
Well, not necessarily. Well, okay. The kernel works more or less better than the rest, and it is expected to. But, well, it's not big secret that we have occasionally, I'd say 1 in 2 years and 1 in 4 years, proof of false. So it's clearly symptomatic that there had been a bug in the kernel. So the kernel is not bug-free, even if we try our best to provide it this way. But as I said, we are involved in trying to certify this kind of code. And we do have a certified version by Bruno Barras. The problem is that what is certified is not exactly Coq itself. And for instance, there's no those teeny optimizations, things that we do like for our everyday life. And so what he has certified cannot be just copy-pasted in place of the current kernel. So how to bridge the gap between what we can today certify and what we today like as implementation? Well, that's an open question, and we will try to do it. But okay, so just to conclude on a more optimistic answer, well, those kernel issues are really, really rare, I would say, compared to, as I said, the not found exception typically in some tactic.
Thank you. I suggest we stop here to have a short break. I'm very glad to see you.
Thanks again.
Discussion.